Hey there, and welcome. Have you ever just stopped and wondered, how do we predict something as wild as a hurricane or as precise as a planet's orbit? Well, it's not magic, it's physics. And today, we're going to crack open the physicist's toolkit and see just how we build these incredible models of reality. Let's dive in. Right? That's the big question. How can one little handful of equations possibly predict something like a planet's orbit and the way honey slowly drips off a spoon? They seem like completely different worlds. Well, the secret is building our models piece by piece, and it all starts with having a language that's precise enough to even talk about the universe. So, before we even get to the why, what's causing all the motion, we first have to get really, really good at describing the how. Where is something? How fast is it going? This is the first, most basic tool in our whole kit. It's all about the language of motion. And the key piece of that language is something called a vector. Now, a vector is way more than just a number. It's not enough to say 5 meters. A vector says 5 meters that way. And that little addition, that direction, is absolutely crucial. Think about it. Everything in physics, from where you are in a room to the force of gravity pulling on you, has a direction. Okay, so here's where vectors get really cool. We can use them to add up different movements. Let's say you walk 5 meters forward and then 2 meters to your left. We can break that down into simple components, just like you see here. Then, with a little bit of basic geometry, we can figure out exactly where you ended up in a straight line from where you started. It's just a super neat, organized way to handle a complicated path with simple math. All right, so now we have the language down, we can describe motion. But what makes something speed up or slow down or change direction in the first place? What causes the change? That brings us to the next tool in our kit, forces. These are basically the rules of the game for how everything in the universe interacts. And at the heart of it all is this one beautiful rule, F equals ma. Look at it. It's so simple, but it is unbelievably powerful. This little equation is the magic bridge, right? It connects the invisible world of pushes and pulls, the forces, to the stuff we can actually see and measure, the acceleration, the change in motion. This right here is the engine that drives all of classical mechanics. And here's the best part. Using this rule isn't just some random guesswork. It's a clear step-by-step process. First, you figure out all the forces acting on something. Then, you draw a little diagram to get everything organized. After that, you just apply F equals ma to each direction, up, down, left, right, separately. It's a method that turns what could be a really messy problem into a totally solvable puzzle. But, okay, here's where we hit a snag. Everything we've talked about so far, it's been in this perfect, clean, idealized world. No air resistance, no friction. But what happens when we try to apply these rules to the real world, the messy world where things get, well, sticky? Yeah, to make our models actually useful, we have to start accounting for all those real-world forces that are always trying to slow things down. And that means we need to talk about friction between solid objects and what I think is even cooler, viscosity, which is basically friction inside of a liquid or a gas. This table really lays it all out, doesn't it? On the one hand, you have our simple, ideal model. Objects just move forever in a vacuum. Fluids flow perfectly. But on the other hand, you've got the real world. You have friction, you have air drag, and fluids have this internal stickiness and create these weird, complex layers when they flow over a surface. If we want to model that honey or the air flowing over an airplane wing, our toolkit needs an upgrade to handle all that. And that stickiness has a name. It's called viscosity. You can think of it as internal friction within a fluid. It's the reason honey is so thick and resists flowing. It has high viscosity. Water, on the other hand, flows easily, so it has low viscosity. This one single property is pretty much the key to understanding why real liquids and gases are so much more complicated than our simple model. So, how in the world do we deal with all this complexity? Well, we need to bring out the big guns. We need a much more powerful tool. It's kind of like the master key for all of fluid dynamics, a set of equations that's built to handle the messiness of the real world. I'm talking about the Navier-Stokes equations. Now, don't worry, we are not going to put the actual equations up here. They are notoriously complicated. But what really matters is what they do. Just think of them as a superpowered version of F equals ma, but specifically for fluids. They take everything into account: the fluid's velocity, changes in pressure, that internal friction or viscosity we just talked about, and even outside forces like gravity. It's the whole shebang for modeling how fluids move. And here is the beautiful payoff. After you go through all that complicated math, these equations can predict something incredibly simple and elegant. It turns out, for a fluid flowing nice and smoothly through a pipe, the equations predict that the speed of the fluid will form a perfect parabola. It's moving fastest right in the middle, and it slows down to a complete stop right at the walls because of that viscosity. It's just a perfect example of this beautiful, simple order emerging from what seems like total chaos. Okay, we're almost there, but the toolkit still isn't totally complete. Think about it. Motion, forces, friction. All of these things involve energy, right? When you push a block across the floor, friction creates heat. When a fluid flows, that internal viscosity dissipates energy. So to have a model that's really complete, we need one last tool, the laws of thermodynamics. The first law, at its core, is basically the ultimate rule for energy bookkeeping. It just says that energy can't be created or destroyed. A system's internal energy can only change in two ways. You either add heat to it, or the system does work on something else. It's what connects the world of mechanics, work and forces, to the world of heat and temperature. And once you add this final piece to the toolkit, wow, it becomes so much more powerful. Now, we're not just modeling how things move. We can model how they heat up, how they cool down, how energy gets converted from one form to another. All of a sudden, we've gone from just describing billiard balls on a table to describing how a car engine works or even how a star shines. I love this quote because it really gets to the heart of what it means to be a physicist. It's not just about knowing the rules, it's about knowing when and where to apply them. Yeah, our super complex model for viscosity is absolutely essential right near a surface, inside that boundary layer. But once you get far enough away from the surface, our simple, ideal model works perfectly fine. The real art is knowing where your model works and where it breaks down. So there you have it, an amazing toolkit for building models of our reality. But, and this is the exciting part, it's not done, not by a long shot. There are huge mysteries out there, from the bizarre quantum world inside a black hole to the puzzle of dark energy that our current tools just can't handle. And that just leaves you with this incredible question, right? What will the next brand new tool in the physicist's toolkit even look like?